This is an example, a little more real example of how you can visualize these networks. So right here, I've got my inputs, uh, and this is how the coordinates work in 2 dimensions, just to be able to have a graphic visualization. But you can have many more entry dimensions. In this case, we just have only 2 hidden layers. So this platform allows to configure all of this. So these 2 that are here can be configured, have hyperparameters. So I've got my 2 layers and I have my output here. So generally what you have to do in the training process is that I separate a part of the data, like validation data, and I do my training, and I'm also validating at the same time, doing the calculation of the error in my validation data. So I'm going to have 2 curves here, one for the training data and the other one for the validation data. And you can press play here in the platform to do the training, and you'll see that these connections and the weight of these connections is going to change. So the ones that are thicker are the ones that have more weight, and it makes a lot of sense, obviously. This is if this is very similar to what I want to have in the output, obviously it's going to have more weight because it's got a higher correlation. So these are the weights, as I said before, and this is the part where the optimization occurs, when you start to learn in this process, and this is the output. So this is a very simple example where I have an input, a variable here that's correlated, and that most of the weights are related to it. And here you can see this item here, that's the bias. So each one of these is a neuron, and every column represents a layer, and each one of the connections represent the weight and the operations that are performed between one neuron and the other. So this is one simple example. It didn't require any more layers because I have an input that's directly correlated, so I don't need too many interactions. Now, if we use this example, now I'm selecting this one that's a lot harder. It's non-linear, it does not have any correlations here, so it's going to require of a lot more interactions. So I'm using a larger amount of layers, 6 hidden layers, and and the number of neurons in each layer can be changed, and all the weights can also be seen a little bit better distributed, and how they transform in time until reaching this point. And you can see that this is a harder training, because a small and slight change in the weight and will render everything that has been learned useless. So the seek for optimal parameters is harder. There are minimum local points where the model stays just like it is, and it's hard to find a global minimum for this function. So probably you have to let it run for a long more time to reach something better. So I recommend to go to this link, and you can try and change the values of each one of the parameters to really understand better how this is performed. Another important thing is that if I use a very large amount of layers or neurons in a layer, and I don't have the variables that are correlated in the input, what can very often happen is, like, these models are very powerful. What can happen is that there's over adjustment. So what happens if we are using a linear model that does not have the capacity to model all the data? Well, a model was used that's more proper, and by and if I can classify better. But if I use a complex model, it's going to classify in a very perfect way all my training data, because everything's perfect here, but clearly some things make no sense. And if my data has noise, then my model is going to learn more from the noise than from the pattern that it should learn from. That's behind this. So this is something very important to take into account in everything that's being done when you apply these methods for machine learning. And I had already mentioned uh, in correlations that when we have spatial correlations, we have to be even more careful because many times the validation data are left correlated with the training data because of the spatial location. So once again, be careful with that.